The prevailing belief among most scientists is that the Big Bang theory is the first explanation for the origin of the universe, which includes the formation of stars, planets, and all life on those planets, including ourselves. Although the name may sound strange, the Big Bang describes the phenomena that have happened. In the beginning, the universe was compressed into a smaller area, smaller than the head of a pin, with dense particles. From this small point came the great explosion of matter known as the Big Bang. This event, which took place billions of years ago, set the stage for the opening of the world's history. However, the advancement of scientific data has led to increasing contradictions with the predictions of the Big Bang theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space observatory ever built, scientists predicted that the observations would strengthen the Big Bang theory. Unfortunately, after only 1 year in space, the telescope has surprised scientists with its unprecedented ability to peer deep into the ancient universe. The incredible capabilities of the James Webb Telescope have revealed ancient galaxies that challenge our understanding of the universe's origins. This discovery gave rise to the ability to explore the past before the Big Bang. One pivotal moment in this quest occurred when astronomer Rohan Naidu, working with data from the telescope, stumbled upon a galaxy dating back a mere 300 million years after the Big Bang, making it the oldest galaxy ever observed. Naidu's discovery sent shockwaves through the scientific community, underscoring the transformative potential of the James Webb Telescope. Its mission to revolutionize our comprehension of the cosmos has just begun, promising to unveil unprecedented insights into the earliest epochs of the universe's existence. This epoch, scarcely explored before, holds the key to understanding the formation of the first stars and galaxies. The telescope's findings have defied initial expectations, revealing galaxies with characteristics surpassing previous predictions. This unexpected abundance of early galaxies has ignited a flurry of scientific inquiry, challenging researchers to reconcile these observations with existing theories. As scientists grapple with these discoveries, they confront profound questions about the fundamental nature of the universe and the forces shaping its evolution. Furthermore, the James Webb Telescope's technology is revolutionary. Stationed 1.5 million kilometers away from Earth, shielded from terrestrial interference and cooled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments designed to uncover details of cosmic dawn never before observed. This epoch, known as cosmic dawn, occurred no more than a few hundred million years after the Big Bang, marking the period when the first stars and galaxies began to form. The process by which this occurs is the subject of intense research, with theories ranging from the influence of dark matter and dark energy to the interactions between stars, gas, and dust. Cosmic dawn's observations of galaxies will give scientists a unique opportunity to test their understanding of these underlying phenomena. By examining these ancient galaxies, scientists can confirm the validity of their current models or uncover gaps in understanding that may lead to profound new discoveries. Initially, this telescope was supposed to find only a few faint and small galaxies in its experimental surveys. However, reality far exceeds these expectations. The first telescope images of a distant planet revealed a number of galaxies with numbers, sizes, and luminosities beyond all predictions. This surprising abundance of early galaxies started a race among astronomers to set a new record for the first known galaxies. Every day there is a claim of another record discovery that surprises the scientific community and rethinks our understanding of Earth's history. Since the discoveries of the James Webb Telescope, theorists and observers have tried to explain the existence of these unexpectedly mature galaxies. Some believe that errors in the telescope's analysis of early observations are the reason for these strange observations. However, the consensus remains that these findings represent a paradigm shift in our understanding of the early universe and offer tantalizing clues about the nature of cosmic evolution. The recent revelations from the James Webb Space Telescope regarding early galaxies raise profound questions about the nature of the universe and challenge the assumptions of standard cosmological models. While some scientists speculate whether these observations can be reconciled with existing theories, others suggest that they might be the first indications that the universe is even more intricate and peculiar than previously imagined. At stake is nothing less than our fundamental understanding of how the orderly universe we know emerged from primordial chaos. The early findings of JWST have the potential to rewrite the opening chapters of cosmic history, shedding light not only on distant epochs and faraway galaxies, but also on the very existence of our own Milky Way galaxy. According to Mark McCaughrean, Senior Advisor for Science and Exploration at the European Space Agency, you build these machines not to stabilize the model, but to break it. You never know when it will break. The origins of JWST can be traced back to the Space Telescope Science Institute in 1985, before the launch of the Hubble Space Telescope. At that time, Garth Illingworth, the vice president of STSCI at the time, was tasked with predicting what would happen after Hubble. Despite initial reservations, Illingworth and a small team began preparations for the next space telescope, to be named JWST after the former NASA administrator. Unlike Hubble, which observes visible light, JWST was designed to observe in the infrared spectrum, allowing for a deeper look into the universe. This ability is important for studying early galaxies, whose light has been stretched into the infrared by the universe, beyond the reach of telescopes like Hubble. With its large, cold star-like reflector, JWST is the perfect tool to unlock the mysteries of the universe. The need for JWST was highlighted in 1995 when the Hubble Deep Field observations discovered many galaxies in what was thought to be a void in the sky. The discovery pointed to the richness of the ancient world and reinforced the importance of telescopes that can probe deeper into the history of the world. After more than 2 decades of development and a cost of nearly $10 billion, JWST will finally be launched on Boxing Day 2021. In July 2022, it will be ready to begin its first year of scientific observations. Early programs such as the Early Emission Survey of Cosmic Evolution and the GRISM Lens-Enhanced Space Survey were designed specifically to search for early galaxies. Although initial expectations were low, the results exceeded expectations. JWST's observations challenged previous assumptions about the early universe, revealing galaxies that defy conventional models. These surprising discoveries demonstrate the importance of pushing the boundaries of scientific discovery and demonstrate the transformative power of advanced technologies such as the James Webb Space Telescope. As scientists continue to uncover the mysteries of the universe, they are poised to rewrite our understanding of the history of the universe and the forces that shaped our universe into what we see these days. The first observations made by the James Webb Space Telescope surprised astronomers by revealing very distant galaxies very close. Before JWST, GNZ11 was the most distant galaxy, discovered in 2015 at a redshift of 11 degrees, which corresponds to the age of the universe of 400 million years. However, since JWST's observations began, the GLASS team led by Rohan Naidu and another independent team have discovered it. They identified a galaxy called GLASS Z13 at a redshift of 13, about 70 million years earlier than GNZ11 in the universe's history. These observations were made quickly by simple redshift estimation methods, which, although less accurate than direct measurements, allowed for a rough estimate of the galaxy's distance. Surprisingly, GLASS Z13 appeared unexpectedly bright and massive, already containing a stellar mass comparable to billions of suns, despite being significantly younger than the Milky Way. Subsequent observations revealed even more astonishing findings. Dozens of galaxy candidates with estimated redshifts as high as 20 emerged, indicating their existence a mere 180 million years after the Big Bang. Some of these galaxies exhibited disk-like structures, a feature not expected to manifest so early in cosmic history. Furthermore, evidence emerged for galaxies comparable in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid developments challenged the predictions of the standard cosmological model, lambda cold dark matter, lambda CDM, which describes the universe's evolution based on our understanding of dark energy and dark matter. According to this model, galaxies of this size and brightness should not have formed early in the universe's history. The origin of giant galaxies in the early universe is a great puzzle for astronomers. To understand this problem, it is necessary to understand the beginnings of the evolution of the world. In the first seconds after the Big Bang, the universe was a hot and dense soup of primordial particles. Over millions of years, the first stars began to form, forming the building blocks of galaxies. This process of cosmic evolution, from chaotic beginnings to the structured cosmos we observe today, is thought to have taken approximately 1 billion years. JWST observations challenge this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of observing numerous small protogalactic fragments merging to form larger galaxies as predicted by current models, JWST has detected galaxies that are already sizable and luminous. Follow-up observations with instruments like the Atacama Large Millimeter Array ALMA in Chile have provided further evidence supporting the authenticity of these distant galaxies, ruling out the possibility of low redshift interlopers. These groundbreaking discoveries open new avenues for understanding the early universe and may necessitate revisions to our current cosmological models. JWST continues to revolutionize our understanding of Earth's history, challenge our assumptions, and push the boundaries of astronomical exploration. The lack of dust seen in the observations made by the Atacama Large Millimeter Array, ALMA, indicates that these ancient galaxies are largely untouched. This pristine condition, free of interstellar dust clouds, allowed JWST to capture high-resolution images of galaxies. The telescope's infrared instruments are excellent for this purpose, as infrared light is emitted in interstellar gas and dust that blocks observations in visible light. In addition to infrared observations, JWST's near-infrared camera NIRCam is important in identifying these galaxies. The expansion of the universe over billions of years stretches the wavelengths of light emitted by distant galaxies, a phenomenon known as redshift. NIRCam's ability to detect this redshift is important in identifying early galaxies. JWST's deep observations have revealed surprisingly complex structures in these ancient galaxies. Some show spiral arms, a feature not expected to appear so soon after the formation of the first stars. Others show signs of intense star formation, challenging existing models of galaxy evolution. As JWST continues to collect data, astronomers are focused on uncovering the mysteries of the dark universe.